Hello everyone, welcome to our brownfields module funnel project video demonstration. In this presentation, we will be navigating through the complexities of brownfield software development within the realm of robot worlds. So for this project, the elements assign different code bases randomly to each team, reflecting the variability encountered in professional settings. Within these code bases, we encountered varying degrees of completeness, code quality, and design, which mirrors the challenges that developers face daily. The world server serves as the backbone as it constructs the world, populating with obstacles and artifacts, while orchestrating the movement of robots. As robots from client programs connect, the server manages their interactions, updating the world based on their actions. On the other side, we have the robot client, which acts as an interface between users and the virtual world. Upon connection, it deploys a robot, relaying commands and receiving updates on its status. To facilitate seamless connection, all teams had to adhere to a protocol which ensured interoperability between client and server, enabling the robots to navigate different worlds effortlessly. So for this presentation, I have my team members working with me, and my name is Asanda Zondo, and I'm also working with Nelisa Dlalisa, Bokang Makebinye, and Atuli Ntintili. So for our section A, we will be focusing on the software development source files. To ensure that we are managing our software development source files appropriately, our team used Git as a version control tool. This means that we use Git to track changes to our files and ensure that the correct versions are identified. And as you can see, our source code is actually stored on GitLab, which utilizes Git as its core version control system. This ensures that we can revert to previous versions whenever we need or want to. This also makes sure that all our additional files, such as documentations or config files, are correctly identified and included in our project. So, when retrieving and updating source files, our team followed a structured approach to making changes. This was done by utilizing branches. As you can see here, we have the main branch or the master branch. So what happens is that each team members could create different branches to work on different features independently without interfering with each other's changes. As you can see here, you can go here and see the members that were working on these projects. So this would actually ensure that our updates are made in an organized manner. This reduces the risk of errors and ensures that we are consistent across our project. Also, utilizing a version control tool like Git protects our source files from loss during updates. Even if something goes wrong during an update, we can easily revert back to previous versions of the files. This provides an added layer of security and ensures that our code base is also safeguarded. As you can see here, you can come here and see the commits and the commit history of the entire project. Finally, We also use Git to prevent simultaneous updates by multiple people. Team members can then commit their changes and create merge requests. This will allow team members to review the changes before they are merged into the main branch. This helps maintain the integrity of our code base and prevented conflicts, and thus reduce the risk of data loss or any inconsistencies.
Hi, my name is Atule, and on this part of the video, we'll be going through our coding design conformances and documentation consistency on our robot worlds project. And briefly, Robot Worlds is a program which allows multiple PCs to connect to one server and challenge each other with their own robots. Me and my team were tasked basically with an existing code base to implement some of the missing features on our Robot Worlds project. So we'll briefly peruse through this README file within the project just to see and outline some of the details. And then we'll go to our project planning and designing, and we'll come back with a brief demo of the program. So let's start with the technologies used for this project. Let's start with the technologies used for this project. So basically, we have here our JUnit for testing and its subsequent frameworks. And for our communication protocol, we use JSON, and also for our programming language, we use Java, and for our databases and database management, we use SQLite 3 and SQLite JDBC. Simply SQLite 3 instead of MySQL, because this is a comparably small project and it does not require a separate server to run on its own. So SQLite 3 was convenient. And for our JSON protocol, as I said, we use JSON protocol, and for APIs, we use a simple JSON API. And for our version control tools, we have a Git, which we're gonna go through after this. And our IDEs are Visual Studio or IntelliJ, either or. And for our testing, as I outlined, we have JUnit. And the prerequisites for setting up and running this program is a simple operational system. Will be any Linux distro. Recommended will be your Ubuntu and your Pop OS and your Linux Mint. And basically, to run this program, and it will be, you just need a simple Linux distro, the 4 GB RAM, and any of the Intel processors ranging from i3 going up. And then we have installation instructions for both the server side and the client side. And we have running instructions for the server side and the client side, which you're going to go back and revisit later on when we're making the demo. I want to start over on this side where we do our project structure and planning. So basically for our robot worlds as I outlined, this is a more of a server-side server-side architecture of a program. So on the server side, we have the responsibilities for the server and its project structure and how it should look like. We have the server is responsible for starting the server and also shutting down the server. And also it is responsible for the interface presentation, and that means showing robots that have joined the server and showing the requests and the responses that it sends to the robots, and supporting commands for the server. The server can also make its own CLI commands and configuring the world, and also removing robots from the world. And the client, okay, before we go to the client, I wanna just go back to our project so we can outline this structure before we can just do the whole gist. As I said, there is a server, a client, and a server. So basically, the server, these are commands. So the server, as stated, is responsible for the actual running of the whole server side, setting up the server, accepting connections from the client, which is method responsible for that. And then from there, it is also responsible for listening for the commands from the server and also sending responses back to the client upon receiving request, and also closing the server and removing robots from the world. As you can see, most of our classes are well documented with doc strings and comments on some particular classes where needed. As stated, so that complies, as I said, the server is responsible for setting up the server, running running the server and accepting connections, listening for instructions and sending requests. And also on the command side, the server also responsible for its own action commands, information commands, and word commands, which we're going to outline later on. Going back to our Miro planning and project, we'll go to the client side, which is responsible for three main things. Configuring itself, meaning that is connecting to the server or disconnecting to the server. Any action commands like your shoot, your setting up of mines, and lastly, the movement commands, navigating through the world. And we'll go back to this side and check those few requirements that were needed. We'll go to the client side and select the client's main class. Like I said, client is responsible for its own configuration, that is your connection and your disconnection, sending of the request to the server, and also responsible for connecting itself to the server and sending those requests to the server and also listening back for responses, basically. So yeah, as outlined, and also on the command side, it's responsible for its own action commands and its own movement commands amongst other commands. And then thirdly, as mentioned, for our planning, we have our issues board on our Git, which is part of our version control as outlined, as stated on the previous README file. So we have here our backlog, which is stories that were implemented post, and then these stories that were already done and are incorporated into the project. As you can see, there's a handful of them. And I would say each and every story that's on the closed section is closed, basically. So going back to our project, we'll do a deep dive now. So basically, since this is a client server-side connection, we would have a stressful situation in which many clients are trying to connect to one server at the same time. That could cause a functionality downfall in a way, and that will cause and will force the server to collapse because of the traffic. So the manner in which we impacted that and try to approach it in a manner that would save us our time and also our resources in the future is a manner of our client is built and architected in a manner in a type of it is responsible for its own connection and disconnection from the server. So the server is not primarily responsible for adding or removing clients from its own socket. So basically, that helps us in stressful testing in a manner of if we can look at the two types of testing strategies that we implemented in our project, your acceptance testing and your unit testing, which is acceptance is more like testing the functionality of a certain aspect of our program, and unit testing is testing single units as it states itself within the project structure itself or the classes. So if we can just look at one example for our launch acceptance test, that is for launching a robot. So basically, the robot is responsible, as we said, this ability of a single client to be able to connect itself and disconnect itself helped us in a manner of managing the state of the server itself and the traffic. So basically, before each and every test is carried out, the client needs to connect itself to the server through a port. And after each and every task is complete, it has to disconnect itself. So that helps manage our stressful situation of having traffic into the server. So basically, also, if I can adjust outline, you could see our project is well documented with comments at certain areas that are necessary and also with doc strings also when necessary. And the naming conventions are followed to a TED and are not that ambiguous. And that's about it. And then we can just briefly peruse through we have unit test for our protocols, our positions, and everything like that. We just look at one instance, which is testing for positions, which test minor parts of our programming structure in our classes. As I said, it's a unit test, it tests unit of our program. So basically, as you can see, this test the position class, which is this class that manages everything and anything that associates with the position of a robot within the world. So basically, we have these small components, or you can say methods, and this position test class, which is a test class, is responsible for testing that particular class amongst other classes within the project. So basically, that's the whole gist of the technical and documented side. We'll go back to our README file so we can just have a brief demo of what the project is expected to do and see if it's doing what is expected of it. So we'll look into back to our README file. And since I've already installed the program, we'll just peruse through this installation. So basically, it's as simple as cloning your directory from our VCS and then cloning it into any directory you would like, and then opening the terminal. And then from there, it's a matter of running the server or the client itself. So you can just run these following commands. This is after packaging your server instance, and then from there you can just run this simple command, and then from there it will set up your server. And from the client side, it's as simple as running your Java Java file from within the program itself. So for the usage of the program, you have one of two options on the server side. So for that, like I said, from the server side, you have one of two options. You can either run it from the terminal using a packaged Java file, a Java file, or you can just simply run it from the Java file within the program structure. So basically running the main function within the server. So basically, for this instance, we'll just do a simple run so we can just show the basic functionality of the program. Like I said, the server is responsible for its own setting up of the world, setting up a port to listen through and send requests, and also adding or removing, adding or manipulating the obstacles within the game itself. And it's also responsible for accepting connections from clients. And it can also take its own server queries, which will run later on after running the client side. So going back to our README file, we'll go to our client side for the usage. As I said, as the client, it's as simple as running our Java file, and then from there, you need to launch the robot into the world. After launching the robot into the world, you'll be able to set up your different, you will be able to run your different commands, like your forward, your back, your action commands, amongst others. So let's do that right now and run our client on the separate thread. And then it's as simple as giving a server ID, which is localhost. It's here, then an IP address, give it a name. And then from there, my robot has a name. Now it's a matter of launching the robot as specified here. So the command is launch, and then I give it the type of robot, and then the shot and the shield. The type of robot is given here. We have three types for this project. So I will do a launch, and then I'll do a shooter, and then I'll give it two shields and two bullets. So basically, we have here an OK result in JSON format from the server. This is the response from the server after sending the command, telling us that our command was okay, giving us the position of the robot and the direction it's facing and the whole state of the robot. Coming back to the server side, we can see that the server received information from the client and also sent back this type of response. Like I said, the client has its commands like your forward command. There you go, forward one, and then from there, change your position, and then gives you the state of the robot. And from the client side, Same thing, received the request, send back the response. As I said, the server itself has its own commands as listed in here, which is your dump command and your restore command, among others. So in the server, you can also run your command, which is one of them is the dump command. And as you can see, it gave you the dump command displays a representation of the world state showing robots, obstacles, pits, and everything that is in the world, basically. So basically, you have everything that is incorporated into the world itself. Everything the size, the robot states, and the type of robots that are there, and everything in between. Basically, the program does as expected from the client side and the server side, and the documentation aligns with what is the project structure itself. And I could say we managed our stressful situations in a manner that is decent and is very reliable and also consistent. So basically, in our documentation within the classes and our naming conventions were fairly as requested and also as optimal as possible. So basically, that's the whole presentation about our code design and documentation. And I hope that covered every aspect of it. And that's it for me. Peace out.
Okay, hi everyone. My name is Bokang Makivinye, and I'll be presenting the database side of Robot Worlds, our brownfield module project, which is Robot Worlds. As you can see on our data, on our database we have two tables, which is the world and the obstacle table. So for our world table, we're gonna have an ID. We have ID for both tables, which has the primary key constraint. So each obstacle or each world will be identified by its ID, which is unique and it's a primary key. Then the world will have a world name, which is unique. We can't have the same world name twice in the world table because in the obstacle table we are using the world name as a foreign key, so it has to be unique, and it creates the relationship between a world and the obstacles. We also have other values for the world, like the width, the height, the visibility, the repair, the reload, which are the settings that will be loaded when the world loads. And for every obstacle, we'll have the X and Y coordinates of the obstacle. We need to store those. We have the size of each obstacle. We also have the type of the obstacle, right? And the world where that obstacle belongs to. Here we can say that both tables are in the third normal form because we can see that each table has a column for every value. So there are no values that are repeating. So it deals with repeated values and values that are not necessarily supposed to be there or they are not really needed. So we can say that it's in third normal form. It's also not referencing anything that is outside of our database or it's in a different format. Everything is in a format that the database should be able to understand. So for the data management issues that we had to be aware of when we were dealing with when we were designing the database was that we had to mitigate the data inconsistency. We also had to deal with data redundancy. So the solution to these two issues was that we implement data normalization from the first normal form to the third normal form, which means that every value should be in its own column, and then we can't have data that is repeating. We can't have data that is outside of our database, or it shouldn't be in a different format. It should be in a consistent format that the database will be able to understand. So that was our solution. There are other data management issues, but for our specific project, for our requirements, we didn't have to worry about any of those because the data that we were storing isn't too big to worry about all the other issues. For now, these are the two issues that we have to focus on. The reason why we chose SQLite over other database management systems was because SQLite would have structure compared to H2, which is an in-memory database. SQLite has structure. SQLite also supports query languages, fully supports query languages, whereas with H2, since it's an in-memory database, it mimics a database, but it's not necessarily a database. Also, even though the H2 has better performance compared to SQLite, we still went with SQLite because the data that we have doesn't necessarily take a lot of performance from our setup. So we still have good performance with either database, which means performance isn't a factor that we had to consider too much compared to structure and the persistence of SQLite 3.
What up, everyone? My name is Nelis Azalisa, and I'll be taking you guys through the SQL part of the brownfields project. But first, let me start off by explaining the purpose of this feature. So basically, it allows you to store and retrieve data from the database. In the case of brownfields, the player will be allowed to store the world along with its obstacles, mines, and pits, and so forth. So we used SQLite. We created tables to store data. We used various SQL queries to store and access data. We used relational databases and therefore have primary and foreign keys in our database. Um, so I have these classes, confirm file, confirm table class, create table class, iDatabase access, which is an interface. I have JDBC access, restore world, and save world. So confirm class deals with confirming the existence of the database file. And if it does not exist, it creates a default one. So it checks by using this if statement. And then we have confirm table class, which deals with confirming the existence of the table um, using this confirm table method. So inside this confirm table method, we have these if statements. The first if statement checks if the world table exists, and this one checks if the obstacle table exists. This one checks if the mines table exists, and then this one checks if the table the pits of tables exist, and then this boolean method is the one that checks the existence of the table, and this method is the one that is being called here inside the if statement. And then we have this create table class with these methods: world table method, um, obstacles table method, mines table method, and pits table method. So the world's table method is responsible for creating the table for world using this create statement. So this statement will create a table with three columns: world ID, which defines the ID, the primary key, and world height, which defines the height, and then this column defines the width. Um, and then this obstacle table will create um, a table named obstacles with four columns. Um, Obstacle ID, X position, Y position, world ID, and constraints to enforce a relationship with the world table. Um, and then we have Minds table method, which is similar to the previous one. It creates a table named Minds that has four obstacles and constraints that also enforces the relationship with the world table. And then this method creates a table named Pit with with four columns and constraints, similar to similar to this one, the minds table and the obstacles table. And then we have this II database access, which is an interface that has these three methods: save world, restore world, and restore world. I'm going to explain further um, later on. And then we have JDBC access class. So this class has two constructors. This one is used for default database. This one is used for database located on disk. And then we have this method, which is void. Basically, it checks, it confirms the creation of the database. And then this method is used to connect to the database. This one is used to close connection to the database. And then the save world, which is used to save um, the world in the database. This one is used to retrieve or restore data from the database. And then this one is used to list all worlds inside the database using this select statement. Um, yeah, and then we have restore world. So restore world is a class that has um, these methods. The restore that has this method to restore world. This statement is used to retrieve info from the worlds table using this statement. And then we have this one which selects used to retrieve info from the tables that hold the objects of the world. And then um, we have save world. Save world, as I said, is used to save data to the database. So this insert statement is used to insert data into the database. So this one is responsible for inserting data into the worlds table. Um, this one inserts obstacles in world into the obstacles table in this statement. Um, and then this one inserts pit in world into the pits table. And then this one insert mines in world into the mines table. And then this method is used for creating data. So um, That's about it.
Hello everyone. In this section, we will be assessing the test plan execution and database access verification in computer program testing. So, for our test plan, our group decided to implement automated tests that validate some of the functionality of the server. All of these methods should be tested by means of unit testing for data access code and acceptance testing for stories. We also define command line arguments to control some parameters for our server, use mock objects or stubs to simulate the behavior of the database by sending post requests to the API. We also do not use Java persistent API for any of the stories. We do this to ensure the consistency and reliability of our test results, as JPA can introduce dependencies on the database schemas and configuration, which makes the test less isolated. We also use the existing data to allow us to simulate real-world scenarios and test the application's behavior under conditions that are representative of the actual production environment. For our use of input data as specified in the test plan, you can see here we have the command line arguments test where we are testing our command line arguments. So as you can see here, we have these arguments that you pass on the command line, right? And then we expect that whenever you don't pass an argument, the default should be the port, which is 5000, the size of 1 by 1 in the world, and no obstacles in the world. And then as you can see here, we have different tests. We test for custom ports and custom well size and obstacles, and that these things ensures that we cover various test scenarios and also ensure comprehensive test coverage. Also here you can see even in this test, which is the machine gun test. Machine gun is a type of a robot. So here we have a new array list of a robot, and then you launch a robot which is called machine gun, and then here are expectations. We expect that it has a shield of 2, 6 shots, and a max shield of 2, a max shot of 6, which is the same as the shields and shots. And then you also expect that it is facing north whenever it's launched, and then the distance that the machine gun robot can see is actually 2. As for deviations from the test plans, we do not expect any deviations. We actually expect that every test should pass for both the client and the server side. And as specified in my test plan, we shouldn't use the Java persistence for any of the stories or for the testing. Actually, this is done for testing and retesting. So as you can see here, our data is cleared from the database when the server gets stopped or is shut down. This thing actually maintains consistency and reliability of our testing processes. To test for our program logic part, we would actually go through the robot test. In this test, we are testing for the robot states. We want to see what actually shows whenever you want to see the robot states. As you can see here, you have to get an array list of the robots, and then actually the world, and then in that world you add the robots, and then here you launched a new robot, you name it Bob, and its type is normal, and then you give your robot a position, and then you also give it direction. And then we have robot number 2. This one we call it Ray, is also of type normal, and then we set the position at position X, which is 10, and Y, which is 10. And then we want to see that actually robot 2 states, whenever you call states, it will actually show you a position of 10, 10 and the direction of north. And then we can also go down and see here we sort of have like a same setting, where you actually have an array, you enter a new world where you add your robot, and then you launch a new robot. We named it Bob, and the type of normal, we gave it an obstacle of 0 and 2, and then we set the obstacle. We also set 2 new obstacles, and then we try and update the position. At first we expect the response to say it's obstructed, because it is the position of 5, but then whenever you update the position to a position of 1, which is 1 step, which means your robot actually takes 1 step, it should give you a success and that your robot is facing south. And then also whenever you update the response again, it should also give you a success. But then when you actually gave it the steps which are actually out of this world, you would actually get a failed obstructed response. And for the elimination of errors that are identified through the testing of our database, we actually have this save command test, which pretty much is a test for a command that whenever that you enter save as a command, your world should be saved in a config file. As you can see here, we simulate the game by providing it with the world configuration, the world size, and actually the obstacles, and then we enter the save command, and then establish a connection to our database. And then as you can see here, right here below, that we actually test that whenever you enter save as a command, our what you get as an output should be that the game world was saved successfully. Yeah. This save command test is actually a way of testing that our tables are actually getting accessed in a correct manner, since our tables are actually created in our robot world database file, instead of them being created separately as an each file, like an each SQL file. We create our tables inside our database class file. So therefore we use the save command test to actually test that our tables are actually getting accessed. Testing the save commands ensures that our tables are actually it verifies that our tables are actually as expected, and that are accessed as they are expected to be accessed. And we can also check here on the save world acceptance test, which is almost similar to the save command test. Here we have a simulation of the save command, which doesn't have any arguments, and then what you should get actually is the results that it's okay, which shows that our tables are actually being accessed and are in the correct environment. Lastly, we can use this to actually ensure that the database stores and returns whatever data that we expect it to return with the queries that we have. This actually proves that our database actually performs the way it is supposed to perform. In order for us to verify that our database actually performs the way it's supposed to perform, we will be looking through the Robot World API test. In this test, what we can actually see is our get world request API request get world whenever we want to get a world without specifying the name of the world. And then here we have the HTTP that the request goes through, which is it's on the port 7000, and then we're getting the world. We expect to get the world size. We expect to get the obstacles as well in a JSON format. So we have to accept equals that the obstacles, the expected obstacles are actually the same as the actual obstacles that you would find in the JSON response. We also expect that you get a response of 200, which means that it's okay. Your request went through. We actually also expect that the content type is in a JSON format. Even with this one, where the name of the world is actually specified, we expect the same thing, that your response will be okay, and that you actually get the world size and the obstacles as well in a JSON format. So if you were to run your API and then go through to this address, you would actually see the JSON of whatever the obstacles were and whatever the world size was. So to execute my test, I will be using Maven test to run all of my tests. I will come here to my terminal. Let me first cd into my client side. So I'll cd to my robot underscore client, and then I would run Maven test. I don't expect any errors to show up. I expect all of my tests to pass. Compilation is taking some time. Okay, as you can see here, there's 10 tests were ran. There were no failures, no errors, and no tests skipped. And then I will go back and then cd to my robot server as well, and then run Maven test there as well. And also here I don't expect any test failures, so it will first compile and then run the test every time you run your Maven test. As you can see here, there were 72 tests, no failures, no errors, and no tests skipped. And then what you can actually do as well, all of these tests are actually stored here on the Surefire reports for anyone who wanna view the reports again, who wanna view the test results. As you saw, all of the tests were passing both on the client side and the server side, so there were no deviation from the test results. There were no deviation from the test plans, as all the tests were passing. So to reproduce my test, I can run Maven test again, and then I expect the same results to show where all the tests are passing. As you can see here, all of the tests it's finished, build success, 72 tests, no failures, no errors, and no tests skipped. This can be achieved for the client side as well. You can just run Maven test and then all of the tests will pass. If anyone wants to review the testing process again, as I mentioned before, can actually come here and click on the Surefire reports folder, which is under the target folder. This is for the server side. You can just come here and click on any of the tests, and then what you can actually see is that the test was run, there was no failures, no errors, none whatsoever. You can just click on any test, and then if the test was passing, you would actually see that there was no failures and no errors present. This can also be achieved on the client side as well. Tests, then the Surefire reports, same thing. There are further improvements that can be made to our testing process, such as stress testing. This can be achieved by just widening the pool of input data, by inputting invalid data, and actually ensuring that it is handled accordingly. What you can also do is by testing more API endpoints and testing invalid API endpoints to actually see how it is handled and make sure that you handle it accordingly. For organization policies and procedures, you can actually see, you can look at our tree here. You can actually see that we have separate folders for different type of tests. As you can see here, we have a folder which only comprises of server commands. These are server commands, and then you can actually see this is a separate folder for our robots, which only tests for the types of robots. And then here we have the one with client commands and so on and so forth. A separate folder for our acceptance tests as well. For example, you can see in this file, these tests are only specific to testing the forward movement only. This one is specific to testing the reload command only, and then we can also these are all in the client command folder, and then also have these API folders. API test, which only tests for the API.